Hello everyone and welcome back to my sixth part of Bitcoin trading bot. In this part, we'll learn what is the simplest way to download historical cryptocurrency market data via exchange APIs. And we'll use this data to train our reinforcement learning Bitcoin trading agent that could finally beat the market. So beginning at algorithmic trading is a popular way to address the rapidly changing and volatile environment of cryptocurrency markets. However, implementing an automated trading strategy is challenging and requires a lot of backtesting, which in turn requires a lot of historical data and computational power. While developing this Bitcoin reinforcement trading bot, I found out that it's quite hard to get lower historical timeframe data. While there are many sources of the market that offer historical cryptocurrency data, most of them have drawbacks. A lot of them require to pay for such data and are not that cheap, and sources for free data provide only low temporal resolution data daily or cover limited time periods of restricted amount of currency pairs. In this tutorial, I will show you that obtaining historical OHCL at 1 minute or whatever resolution you need is actually not a magical task that could be done in a few lines of Python code without spending any penny. So as you can see right now, I have opened a Bitfinex, some kind of document, and in this tutorial I will show you how to use this Bitfinex exchange API to download this I mentioned historical data. However, this approach also works for any other exchange that provides a similar API, but I chose Bitfinex right now. Also, if you don't have a Bitfinex account, don't worry, this can be done without it because we will only use a public API endpoints. In case you are not familiar with that what an API is, how it works, or how to use it, you can read about it on Bitfinex API documentation, as you can see on my screen. This is also the interface through which our algorithm will interact with the exchange. But don't worry, there are already several implementations available. We don't need to write the Python interface for communication. For this, I'll use a simple Bitfinex 10 cars, the Python library, and this is also the interface through which our algorithm will interact with an exchange. But don't worry, there are already several implementations available. We won't need to write the Python interface for communication. For this tutorial, I will use Bitfinex 10 cars, the Python library, which can be installed via pip. So actually here is the GitHub, and we simply need to issue following command, and everything will be installed through pip. It's quite old, 2 years, but it doesn't matter while it works for us. Also, we could use another library like Bitfinex API P, but which allows us to do live trades, but because this tutorial is not about live Python trading, will be better use the Bitfinex 10 cars package actually. So I will explain you shortly how to use this. So if we would look at the Bitfinex API documentation, we will see that there are two API versions, version 1 and version 2. It's more explained here. Both of them are implemented in the client we just installed, but I chose to only use the version 2 API. After importing the Bitfinex API client Python library, we need to create an instance of the v2 API by running the code. So actually I will open my example code. I here wrote a very simple example, and it will be quite easy to understand. Pay attention that we are not providing any keys here, so we will only have access to the public endpoints. This means that there are no ways to somehow risk losing our balance in the Bitfinex account, of course. The corresponding message will be shown after we'll run the code. So here we simply import this library, and here I create an instance, as I said. Here I choose my pair and time frame, and actually this is the line what's the most important, in which does the whole download stuff. So that's quite simple, and this is how we open gates to our historical market data. And from the Bitfinex documentation, we saw that one of the public endpoints is called candles that returns the data behind the candlestick chart that we've seen on the all exchanges. This kind of data contains a timestamp, open, close, high and low price, and usually the trade volume. At first, we'll try the simplest way to interact with the endpoint through the client by just calling the script. Actually, these lines will give us the last 1000 minutes of the OHCL prices in Bitcoin USD pair. That's a nice achievement, but we usually are interested in a time period long ago or different currency pairs. To achieve exactly what we want, we should specify the exact start and end points. So actually, this is the lines where I do this, and as you can see, I here selected simply something wrong. Okay, I selected 1 month, and that's a September, and whatever, and you'll see how simply it works. And I don't want to show you how everything to write, but actually let's run this and you'll see how everything works. So I'll just run it, and as you can see, no keys, only access to public API functions are given, and it plot me the results I downloaded actually, and there is no any formatting, no time frame and so on. This is the price of Bitcoin, and this is the plot you should receive. And actually that's quite simple. As you can see, I can choose whatever time frame I want, and for example I'll choose February, between January and February, and let's run this, and yeah, it downloaded. It doesn't take even a second to download this kind of data. So that's quite impressive and easy solution how you can download this data actually. And that's it. I of course can change this 1 hour to 1 minute, and let's see, it should also work. And this is 1 minute historical data. That's insane. Okay, I'll return it back to 1 hour, and that's it. So now we know how to download 1000 historical data steps, but the question is how to download more data if API can't download more data at once. So if we were to increase the time interval of interest to the entire year, for example, we would not be able to get it at a 1 hour resolution. As you can see, I can write, I want, for example, 2 years of historical data, and it won't give me. I can change it to limit is of 2000, and let's build. And yeah, I think it worked, but let's try a little bit more. Also worked. Okay, I might be wrong, but there maybe were some kind of implementations, and yeah, as you can see, now it's the limit. I was wrong. 10,000 is the limit. So sorry for my mistake, but that's not always 1000. So actually that's great, but what to do if we would like to download more than, as I said, 10,000? So if we were to increase the time interval in the interest the entire year, for example, as I showed you, we should not be able to get it at, for example, 1 hour resolution. So to get past this limitation, we need to write a function that would split our big query into multiple smaller queries. Also, I must mention that we need to keep in mind that there is a limit to how many requests we can make to Bitfinex API. Currently, this limit is 60 calls per minute. That means after each request, we should wait for minimum of 1 second before we start the next call. To be safe, the my written function, I can open the original function. We'll do a 1.5 seconds sleep. As you can see, here is my function, which I'll use to download the full history of data. And as you can see here, I chose 2 years, and I'll download this data pretty fast. Now we can run queries for longer time intervals with this following written function. I'm not going to explain this step by step because, of course, everything requires time and it's not that difficult. And of course, I'll upload everything on my GitHub page, so you could download. Here is the only extra thing that we need to calculate and provide is the step size in milliseconds. Actually, and it's calculated here. Every new while loop, we recalculate the step size to know how many data points we should ask in every new small query. This is very similar to the limit we defined before. In order to reduce the number of calls we do to the API, it would be best to go for the maximum step size. For the 1 minute case, step size can be calculated. So I will show you how it's calculated and here above. And for example, my time is how I calculate time is seconds multiplied by limit by 1000 milliseconds. Okay, so for 1 minute interval, I will do following calculations. I have 60 seconds and I'll multiply it by 1000 and again I'll multiply it by 1000, and this will be equal to 60 millions. And what I do for one hour interval is that I simply can copy this and I'll just write 3600 because 1 hour has 3600 seconds, and this is left as before. So the answer is 3600 multiplied by 1 million. That's it, and this is how we calculate the step size. Okay, I'll remove this now. You don't need this. So finally, we want to convert the results into a pandas data frame. Then we can remove potential duplicates. I actually do everything here. So I fetch data and after remove duplicates and making sure that everything is in the correct order, I can convert it to numerical timestamp into a human readable format. In the final step, we can save our downloaded historical data and save it to a CSV file. Actually, and here is my CSV file, but because I already have it here, where it is here, and as you can see, there's a lot of information. I can run this example, not this, and I'll simply add some endpoint different, and I'll take almost 1 year. It will be fine for an example. So okay, I can run, and this will simply start, and this will download 1000 each 1.5 seconds interval. So if you wonder how many current pairs of historical data you can download through the Bitfinex API, well, actually, you just need to run quite simple commands, and both of these. And you'll get this information. Actually, I'll write this to the text version tutorial. Okay, let's move forward. One of the major problems right now we face with current Bitcoin trading bot is that it takes too long to train it to some kind of satisfying results. Obviously, right now I'm using quite low learning rate. We could train it much faster while using bigger one, but then our model might not learn important price action features. So it's quite obvious that it's some kind we should speed up our learning process. One of the best ways that comes to my head is that we should use multiprocessing. If you were following my past tutorials, you should already be familiar with my Bipada worker with 3 reinforcement learning tutorial, where I used multiple environments to train my agent. So we were creating 16 running environments and we were detecting their next state in a batch. This is the way how we speed it up. I tested that we were not winning a lot of speed while running multiple environments in the background and detecting states for each environment. So in this part, I decided that I need to do similar stuff. So we'll reconstruct our custom environment in a way that we could start multiple of them in a background. This way our bot will have the opportunity to try more different trade combinations and faster learn price action features. But I will mention that I'm not a pro while we talk about Python multiprocessing, but I already successfully implemented it in several of my past projects, as you can see. So first I'll show you a simple example where we'll use a pipe communication between multiple processes, and then I'll show you how I implemented our custom environment in a similar manner. First of all, I'll go to the code, and I'm not going to explain it step by step how Python multiprocessing works. I'll discuss the concept of data sharing and message passing within custom environments processes while using the multiprocessing module. In our case, so here is my example of multiprocessing. In our case, any newly created process environment will do two following steps. First, it will run independently, and second, they have their own memory space. You can see my code example. To understand the basics of multiprocessing, I created a class called environment, and inside is a process that will create an independent process running in the background. For simplicity, my process as a result will simply return the received number multiplied by 2. So here I do a multiplication simply. So I created only two custom processes. As you can see here, I create two of these processes. For communication between the main program and environment, process will be used a pipe. So pipe returns two communication objects, which represents the two ends of the pipe. And here is the parent and child connections. Each connection object has send and receive methods. This is quite simple code, and in the main loop I'm generating a random numbers. Here I'll run a while true loop, and as you can see, it's simply generating numbers for each process between 0 and 10 and sending it. Not to spam my console, I used a 1 second sleep, and then I run another loop to read pipe for answers and print it to the screen. Well, actually we can run this and we'll see that it's not rocket science. I'll run it from terminal, so it will be a little easier for me to kill all the processes, because while we're running it in processing, that's quite obvious. It creates processes in a background. Python multiprocessing example.py, and let's run it. And as you can see, here shows worker 0 and first worker. That's simply an ID of workers, and actually it returns a multiplication by 2, and as you can see, it runs in a loop. In a similar principle works our multiprocessing environment with a custom Bitcoin trading bot. Instead of giving us back a simple number, we'll run our custom trading environment to make a predicted action and return a state, reward, and other parameters of a particular environment. Of course, it's much easier to tell than to convert my words to code, because while programming a script to work with multiple processes, sometimes it's quite complicated to do fucking debugs. But luckily I already did this hard job for you. So simply here is code that we'll use to create an independent environment running in the background. So first I'll close this, and I can open this multiprocessing environment package which I created. Here I'll add dates of today. It's February 8th. Okay, and here it is. As you can see, here is the class that creates these kind of environments in the background and returns state, reward, done, reset, net worth, and episode orders parameters that will help us to track each environment statistics and do proper action prediction actually. So this part is quite complicated, and I think I'm not committed to explain its code, so I'll simply give you a function that we'll use every time we want to trade our custom Bitcoin reinforcement learning trading agent, and the network parameters are defined in the same way as before. Apart from that, now we can set how many workers we want to create with the num worker parameter. So actually here is my train multiprocessing. And as you can see here, we use an agent, number of workers. Here is data set we'll use to training batch size, visualize or not, and so on. That actually all the same parameters. Before choosing the right number of your workers, consider that CPU and GPU you have, because if you have a GPU, you can run more workers, because training will be done on a graphical processing unit and environments will be run on a process. Other way, if you don't have a GPU, you won't get significant speed improvement, because the hardest part is the training, and that will be done on the same CPU where you are doing all your stuff. Anyway, here is the code of training, and as he said, I'm not explaining this. This is simply bigger code from simply this following train function. Actually, that's what's here. We used a train agent function to train, and there is actually similar way, did everything, but it's for multiple workers. But probably you need an example of how to use this function, right? And actually it's not that different as it was before, and I'll give you an example. Here it is how I trained a dense layer. Actually, here is the code I commented from my previous tutorial, but I'm not using it anymore. Well, maybe a train agent test I might use, but not necessarily. So actually we do all the stuff as before, and here is a multiprocessing part, and here I define an agent in the same way as it was here. But right now I'll run train multiprocessing, and here, as you can see, I trained it with 32 workers with actually all the same parameters, and the main parameters you can change are actually the same. This is a lookback window, learning lead, epochs, optimizer, batch size, model type, workers count, training batch size, training episodes, and so on. But actually here is a dense, and I trained it for 3 different models, but let's talk about it later. And if you think that it's a lot of parameters, believe me, here I give only the most important parameters. There is much more that might be changed when we start talking about optimizing our model. But from training and testing results, you'll see that it's enough parameters to create a primary view of a model. And if you were watching my previous tutorial, you already should know that I created 3 different models. It's dense, CNN, and LSTM. So I trained all of them, and I can show you my training results and parameters for each model in the table. And actually I'm not training this on my tutorial, and here I have an images table, and actually here is the training table, and as you can see, here is the model type. Here is a lookback window I used, and actually these are quite similar parameters. Well, here with LSTM I used a batch size of 128. Well, actually to reduce a training time. Otherwise it would be even 2 or 3 times longer. As you can see, even now it's longest. As you can see, I mostly try to change model type and window size and batch size. As a result, I look to my best model score, that is here, and training time, as I already said. From this data, you can make your own opinion on which model is best. I lean towards the convolutional neural networks. Of course, LSTM is also quite impressive, but it requires more than 2 times longer training time. So actually, I can give you a TensorBoard snip. I have it here. I'll add these images to my text version tutorial, but for this tutorial I simply made them. This is all 5 models. I wrote here what is the model according to the colors, and you can make your own opinions. You probably don't understand what is this actor and critic loss and what does it mean. So actor loss gives us an average size of the actor loss function, and it actually correlates to how much the policy is changing. This should decrease during a successful training session, and this value is as it is. Actually, it is decreasing. At first it's growing, and then it starts to decreasing. But convolutional neural networks, as you can see, are below 0, while dense and LSTM are above 0. That's I can't explain why, but that's how it looks. And these values will fluctuate during the training. Generally, they should be less than 0. Than 1, as it is. And similarly, the critic loss is the average size of the critic loss function, and it correlates to how well the critic model is able to predict the value of each state. This should increase while the agent is learning, and as the reward stabilizes, it should decrease, and critic loss will increase as the reward increases, and when the reward becomes stable, the loss should decrease. But actually, because this is not the standard environment where there is some kind of limit or higher scores, but right now there is an unlimited scores, and every episode our agent might do better and better orders, because theoretically it might be overfitting to data. So while trading, it might never be stabilizing but always only increasing. So I don't have yet an idea how to find this point where our model starts overfitting. So actually you can make your own opinions from these training results, and it's quite hard to guess what model will be the best with validation data, but we can assume that it should be with the best model score. So it should be CNN or LSTM networks. We'll find out after testing both of them, and you'll see that, of course. No less important is the testing phase, as I said, for us. So I'll also write a multiprocessing script to test our trained model. Here it is. And here's a testing model. It's actually the same, few parameters changed, but actually you can compare this by yourself. And probably the same as with the training part, you need an example how to use this for the testing. And it's not that different as it was before. And here is an example. And I'll upload everything. This is with a trained model, which I'll also gonna give you on GitHub, and upload everything. Well, actually, I'll upload all these best models that you saw in that table. Simply, we call this test multiprocessing on our test F dataset. Most important step, and we set episodes, testing count, give a path to our trained model, and that's it. Actually, testing is much less resource hungry process, so it's not a problem to test all my trained models. Of course, and results are also given in a following table here. I must note that these results are for unseen data. Our model never saw it. So, as I said in my previous tutorial, the most important parameters are no profit episodes and ending net worth. As you can see here, looking at them, we can evaluate how good our model is. In the following table, I highlighted the CNN model that had the highest ending net worth on our testing dataset. In 3 months, this agent grew our net worth by 48% actually. And if we average this number to each month, that's around 60%. That's impressive. And in the previous tutorial, we saw that CNN wasn't performing that well, but I thought that this might be because of short training data. And my theory was confirmed. We needed more training data. And that's it. I'm not showing you stuff as in my previous tutorial. I'm not giving you some kind of GIF or so on, because we are interested in our results. And actually, they are great. So, retrieving high resolution OHCL data is actually not that complicated, and it's much easier to use Python script and download it than Google it for hours, where you can download it for free. So I proved that actually it's possible to beat the market with neural networks. However, I'm still skeptical about running it for live trading. At least I do not want to recommend it for you. There is still a lot of stuff where this bot could be improved. So far, trades in our simulation are taking place on perfect terms. So in the next tutorial part, we'll add fees to all trades we do. Also, maybe we'll add much more indicators that our model could learn more market features. And also, I think that my data normalization technique is not the best. So I hope to do some kind of investigation into this part, how differently I could do this normalization and so on. So thank you all for watching. Thank you all for these likes, and if you didn't give me a like for this video, so smash it right now, subscribe, press that bell button, and as always, all the code given in this tutorial can be found on my GitHub page and it's free to use. So if you have any comments, you can write. If you have questions, you can write, and that's it. So thank you all for watching and see you in our next part. Goodbye.